not sure how Professor Zhang Qing introduced photoelectric effect, but I feel that there's a picture that you should understand. Once you see this picture, what we call the energy band diagram picture, you should be able to understand photoelectric effect quite well. Okay, we know that in any metals, there are many electrons because metals are characterized by having high conductivity, and that comes about because there are many electrons. Now, if you look at the energy of these electrons, they have a very wide spread of energy. And the energy can occupy from very, very low up to a maximum level, which we call the Fermi level. So the Fermi level represents the maximum energy that you can find for electron in a piece of metal. Is it clear? Now, there's one very important energy level called the vacuum level. Vacuum level represents where the electron becomes free, coming out of the metal. Okay? So, if you want to free electrons from a piece of metal in a photoelectron effect, the minimum photon energy you need to provide is this difference, E vacuum and EF. And that difference is called the work function. Okay, so this difference is called work function. And the photon energy that corresponds to the work function, that particular frequency is called the cutoff frequency. So therefore, cutoff frequency represents the lowest frequency needed to free electron. Because for that particular frequency, the energy is just equal to the work function. Now next, let's consider that we have a photon energy of an amount that is greater than the work function. This photon energy can free electrons in a number of transitions. So for example, electrons at the Fermi level can be excited up by HF. So now it's beyond vacuum level, it becomes free. Electrons that are further down can also be excited by the same HF and get free also, so long as it's cross the vacuum level. So as you can imagine, there are many different electrons at different energy level that can be excited by the same photon energy. And the last transition happens such that when the electron is just excited by the HF, it reaches just the vacuum level. Therefore, there are many different transitions available. Have you all looked at this picture before? Yes, in the lecture notes? Something similar? Okay, in any case, now, so when you have a photon energy greater than the work function, all these electrons can be free. And the energy in excess of vacuum, all this becomes the kinetic energy of the electron. Okay, whatever that is used to overcome the so-called barrier, the excess becomes kinetic energy. So from here you can see that the maximum kinetic energy happens for this transition. For electrons that is at the Fermi level. When it's excited, it will have the maximum excess energy, maximum kinetic energy. So when electrons are emitted, there will be a band of energy starting from 0 up to K max. Okay? Is it clear? Okay? Now from this transition, we can write one equation. Photon energy must be equal to the work function plus K max. And the maximum kinetic energy can be measured in the experiment by applying a decelerating potential. You apply decelerating potential until you don't detect electron anymore. So that potential, when it happens, is called the stopping potential. What it means is that at that particular potential, the energy that the electron loses must be equal to K max, so that even the most energetic electron fail to be detected. Okay? So in fact, now you're already seeing all the equations needed to solve photoelectric effect. This one, HF is Kmax plus work function, Kmax is EVS, and phi equal to HFC. So with these three equations, you can solve all photoelectric effect questions. So let's look at this particular problem. We shine light of the same frequency onto two different metals, and I apply this equation. Okay. So Kmax is EVS. So for metal 1, it has a work function of 1, stopping potential of S1. Metal 2, work function of 2, stopping potential of S2. And you are given that the stopping potential of metal 1 is higher than metal 2 by 1.48. Okay, so what we do is that in this equation, let's multiply by E, electronic charge. So once you multiply by E and then you manipulate with equation 1 and 2, you can obtain a relationship between the work function of metal 2 and metal 1. You obtain 5.2 minus 5.1 is 1.48 electron volt. Okay, I think that one you can try by yourself. Just multiply this equation by E and then manipulate with the equation 1 and 2. After that, you are given that the cutoff frequency of metal 1 is 60% of metal 2, so it's 0.6. You multiply both sides by Planck's constant. So from there, you obtain that the cutoff frequency of the stopping potential of, the work function of metal 1 is 0.6 of metal 2. So therefore, you obtain another equation. You solve this equation and this equation simultaneously, you can find 5.152. So you solve the problem. Is it clear? Here I just show you the work function of different metals. Now, just for information, work function is like a fingerprint of a metal. Each metal has its own unique work function. So therefore, you can find from internet the work function of different metals. Right? So I'll show you here. In fact, from the work function, you can identify what metal is that. Any question? No? Okay, if not, then let's move to question 5.